Hi everyone, welcome to PrepFusion, and this is the lecture 12C for the state space chapter. So this part of the lecture we have been extended to C actually because we couldn't complete in our time. So in this lecture, right, we'll study the parallel and cascade decomposition of the transfer function, right. In previous lecture, what did we study? We studied the direct decomposition of controllable canonical form, then the direct decomposition of observable canonical form. What do we mean by controllable and observable? We'll learn this in the next few lectures, right. So let's start with our lecture. So firstly, what did we study so far? Yeah, as I told, right, we studied direct decomposition of CCF and direct decomposition of OCF. Now in CCF, right, what is the most important thing that you need to keep in mind? That whatever my state variable is, the differentiation of the state variable, it is always equals to the next state variable. So for this case, my x1 dot t should be always be equals to x2. If x1 t equals to x1 t is at the rightmost end of the state diagram, okay, then always the next state variable will be related like this one, okay. So yeah, that was the main thing for CCF. Now what will happen in parallel and cascade, right? So in parallel, right, we'll convert the transfer function, decompose the transfer function such that I get my system matrix as a diagonal matrix, which will be very, very useful and helpful, okay. And after converting all those things, my C and B matrix will tell me about the behavior of the system, okay, how we'll learn in the next few lectures. So that's why this parallel decomposition is very, very important, okay, very, very important. Now what is cascade decomposition? So cascade is just two blocks connected in cascade. So I will divide the transfer function into multiples of two, multiplication of two transfer functions, individual transfer functions, and I will just place those state diagrams right there, and that will be my cascade decomposition. So this is very easy, and I don't think this will come, but this is difficult, okay. And in this parallel decomposition, right, in parallel decomposition, two things may happen, right. So as we learned, right, in eigenvalues and eigenvectors chapter, what happened, that we can't simply diagonalize any matrix, right, because for us to diagonalize, first is if the eigenvalues are distinct, then obviously we can diagonalize, no issues with the matrix. But if the eigenvalues are repeated, okay, it may so happen that the eigenvectors are dependent on each other, they are not independent, then we won't be able to diagonalize that matrix, okay. Then this parallel decomposition will have two cases: one where the eigenvalues are distinct or the eigenvectors are independent, right, and other one is where the eigenvectors are dependent. Then we'll have to convert this into some other format that is known as Jordan format, okay. So yeah, Jordan matrix format, and the first format was diagonal matrix, right. Diagonal matrix will know only the diagonal elements will be present, where we'll have only what do we say, the eigenvalues, right, okay. So that is it for just the introduction. Now let's start with the parallel decomposition, okay. So here, as I told, right, so what we'll convert into two forms, either the diagonal canonical form or the Jordan canonical form, okay. Jordan canonical form is just like a diagonal canonical form, just it is a bit different because the eigenvectors are not independent in this case. So let me write here. When the eigenvectors are independent, okay, and we'll convert into Jordan when the eigenvectors are dependent. So this is basically the two things that that I wanted to say to you, right. So yeah, now let's using a question we'll understand what is the parallel decomposition. So we have been given a question where it has told us that For the block diagram, we have been given a block diagram given below. Find the transfer function. We have to find the transfer function. Okay, this is wrong. This will be actually r. Okay, one more thing I have to tell you is that, like, sometimes what I will do is I will take the input as u of s and I will take the input as r of s. This one, right? This can be r of s, u of s, whatever variable you want to name, you can name it. Okay, but you don't get confused, okay, with u of t. Okay, because u of t is unit step, but they will mention, okay, if this is given as u of s, then you should understand it. This is not unit step, this is an input, right? So yeah, different books use different references, so just be mindful of that. So I wanted to warn you that you shouldn't get confused with whether u of s is written, r of s is written, or whatever else variable is written, right? What you should understand is this is input and this is my output. That is the main thing you should understand. If u of t is written, then you have to understand whether that is unit step or not. You will understand. If you are just doing mathematical questions, you will understand. Generally here, right, in control system, if some u of s is written, okay, then it will be input only. Okay, so that is one point I wanted to mention to you. Now we have to find the transfer function y upon r. Okay, so if we have to find the transfer function y upon r, and also we haven't given this values of this h1 block and like h2 block, right, the gains of the h1 and h2 block. Now how are they connected? Tell me, how are they connected? They are connected in parallel basically, right? So as the name suggests itself, so this is parallel decomposition, so they have to be connected in parallel. Okay, so what we will do is they are connected in parallel and then they are subtracted. They may be added also, they may be subtracted also, it doesn't matter. Okay, but the main thing is they are connected in parallel. So we will find the transfer function that we already know from the second chapter itself, how to find transfer function using block diagram, right? But that is not important. After finding the transfer function, we have to do few other things. So first let me like solve it from basics so that you are able to refresh in your mind like what is like how to solve this, right? Maybe you have forgotten already whatever you have studied in chapter 2. So let me copy this one and paste this one, right? So I will use the simple assumption method that here we have r, here we have r, here we have r times h1, here we have r times h2. Okay, here what we have, here we have r times h1 minus h2. So this is what we have at the output. So y equals to r times h1 minus h2. So y of s equals to r times h1 minus h2. Okay, so this was what my y of s is. So what is my transfer function now? What is my transfer function now? The transfer function, right, is y of s upon r of s. Okay, so which is equals to h1 minus h2 of s. Now what is h1 and h2 of s? So h1, right, is 10 by s plus 1 minus this is 10 by s plus 2. So this is equals to simply 10 by s plus 1 into s plus 2. Okay, so this is my transfer function basically. Now like what do you mean by decomposition? So if I want to decompose this, right, if I want to decompose this transfer function, I will do partial fraction, basically this one, right? So yeah, what does parallel decomposition means? Break the transfer function into blocks like this one, okay, and connect this in parallel. So I'm going the reverse direction. Okay, I gave you already parallel blocks and told to find the transfer function, but in parallel decomposition what happens, I want to convert this into blocks like this, right? So I want to go from here to here. Okay, so yeah, that is one important thing, that in parallel decomposition we convert the transfer function using partial fractions and connect those in parallel to add them or subtract them, whatever. Like it's just a negative, right? Subtraction is just a negative times addition, so we can do it, right? So yeah, that's what it is. Now what I will do is divide this, right? Divide this into two transfer functions. So t of s equals to, if I do partial fraction, right? If I do partial fraction, I hope you know how to do partial fraction. So I'll put s equals to minus 1 here, so I'll get 1 10 by 1, so this is 10 by s plus 1. Okay, 10 by s plus 1. And what is this? So if I do s equals to minus 2 here, this is minus 2 also, so I get 10 by minus 10 by s plus 2. That is why it was subtraction, right? So here, right, that is why it was subtraction, as you can see. Okay, So yeah, this is basically it. Now, like, these are, I will divide this into two transfer functions. That is, one will be this one, okay, t1 of s, and another will be this one, t2 of s, okay, t2 of s. So these two will be transfer functions, okay. So now, right, how to, like, okay, they haven't flow diagram, transfer function. Okay, I think they have missed one question, so I think I had to auto write, like, draw the state diagram also, okay. Draw the sorry, I think I forgot to write one question here, that draw the state diagram also, that draw the state diagram also. This will be my, I think, okay, I will write this here only, okay, I'll write this here only. This will be my so okay, whatever question this is, I will mark a name that later. Draw the state diagram, right? So we'll go step by step. Now we'll draw the state diagram, then what we'll do for the obtained transformation. So we'll draw the state diagram. So how to draw the state diagram? So I will add the two transfer functions in parallel, right, like in SFG. But first I have to find individual transfer functions, okay, individual transfer functions. So how I will do it? So individually, right, my t, what is my t1 of s? What is my t1 of s? So t1 of s is 10 by s plus 1, okay, 10 by s plus 1. And what is my t2 of s? t2 of s is minus, it is minus, right? So what I will do is add this, I put this negative here and add this, right? It is minus 10 by s plus 2, okay. So let us solve for t1 of s. So what I will do, I will solve each blocks, like each transfer functions using the CCF, right, using the controllable canonical form, okay. So solve using so let me solve for the first like transfer function. So here, right, t1 of s will be equals to simply 10 by s plus 1. So if I take the highest power common, I get s inverse 1 plus s inverse. Now multiply that state diagram. So this is what I get, s inverse by 1 plus s inverse. This is like y, sorry, not y, what I'm doing, this x naught, right, dummy state variable, x naught of s, x naught of s. Now what is this equals to? So I can assume this as one of the outputs, right? Two the outputs are getting added, so I can input is same only. So assume this is y1 of s by r of s. So you can solve this directly, right? How to solve this? So this is first order, so we will have only one integrator, right? So this is my pen, okay. Now we'll have one integrator, so let's say our integrator is here only, okay, 1 by s. Now, right, what is this equals to? So you should solve this directly now, okay. This is equals to basically minus 1, okay. This s inverse goes in this end, okay. I will not solve it slow now, okay. So this will go to minus 1, okay. This will go to minus 1, and like what else is there? Nothing else, right? Only the input is also coming, input gain is also 1, okay. This is u of s, this is y1 of s, y1 of s, right? And y of 1 of s is what? It is 10 times s inverse 10, right? Or like 10 times x naught of s inverse. So this is like, what is this basically? This is s inverse x naught, and this is x naught. Okay, so what is this? This is basically what do you say, this is 10, right? Gain is 10 because we are multiplying by 10. Okay, so we solved the first state diagram. Okay, now the second state diagram. So second state diagram, right? So the second transformation is what? It is same only, but like the difference is minus 10, and in the bottom we have 10 s plus 2. So this one is minus 10 s inverse x naught of s divided by 1 plus 2 s inverse into x naught of s, right? X naught of s. Okay, so this is our like transformation for the second one, right? So again, right, how I can write this? So I can write this like this: y2 of s by r of s, right? Input is same, right? Input is same, but like output is getting added, so the second output. So again, I will like just copy this because this will be the overall overview will be same, but the values will be different here, right? We'll have minus 2, right? I hope you understand. These 2 will go this side, so this will be minus 2. So this will be minus 2, and this gain, right, instead of being 10, it is minus 10 now, minus 10 s x naught s. So it will just be minus 10, and the input, right, input is 1 only because 1 is getting added with it. Okay, like input is here only, is 1. So yeah, this is my second state diagram. Now how I will connect these basically, right, what I will do is connect them in parallel, right? Parallel. So one over there, another, just like the block diagram. Just the block diagram is getting converted into state diagram. Okay, as I shown it to you, right? So this one, right, this is 1 by s and this is minus 1. Okay, so this is y of s, this is r of s, and this one was the first one, and second one will be connected like this. And let me copy this again. Okay, copy this. Here, like from here I got plus 10 gain, from here I got minus 10 gain, and this gain was minus 2, and this is 1. Okay, and this is also 1. Okay, so yeah, this is basically my, this is also 1. This is basically my state space diagram. Okay, basically my state space diagram. So let me write this: state space. As you can see, we're just converting the blocks into state space, right? And they are connected in parallel. Okay, so yeah, this is my state space diagram. So now, right now, what you have to do is write the state space equation. So this is my like that question that I was looking for. So we have to write the state space equation for the state diagram from the previous question. Okay, so how to do that? Again, that follow the simple steps, right? Again, we have to name the state variables again, remove the initial conditions, and then remove the integrators, right, as we have already taken the effect of them. So this is, so what is this? Let me name this as x1. So this will be what? This will be x1 dot, and if this is x2. Okay, these are nodes, so I should name this as also nodes. Okay, this is also node, this is also node, this is x2 dot. Okay, this is x2 dot. Okay, so these are my basically state diagram. Now what I have to do is to remove the 1 by s terms, right? So I will slowly remove the 1 by s term as I have already taken the effect of them. So this is my like state diagram for the writing the state equation. So what I can do is write this directly now, right? So you have to be fast in exam also, you have to be fast. Okay, I have only two state variables x1 x2 as the or like order of each transformation is 1, but overall transformation order is 2. Okay, so here if you see, okay, what was transformation, whole transformation, it was s plus 2 into s plus 1, right? Here, right, s plus 2, that's why we are getting two state variables. Okay, so that is the reason. So okay, now I will write this directly. Now what is my x1 dot equals to minus x1 plus r, right? And this like x2 doesn't have a forward path for x1 dot, so it is minus 1 0. And what is x2 equals to x2 dot equals to minus 2x2 and plus r, but x1 doesn't have any forward path, so it is minus 2x2. And the relation between b u is 1 1, like both of them are getting added with u, right? So both of them will be 1 1. So this is u, I can write u or whatever, like this is r, right? So I can write r of t here. Okay, now about y of t. What about y of t? So y of t, right, y of t is this one. Okay, this I should have written, the gain here is 1, the gain here is 1. Okay, at that previous stage also I didn't written, so gain here is 1. Okay, gain here is 1. So what is y of t equals to? Y of t equals to this both of these variables, right? Any u doesn't have any forward path because like here this is against the flow and this is also here against the flow. So x1 into 10, x2 into minus 10. So y of t equals to 10 minus 10 x1 x2. Okay, so this is what our y of t is. So this is my basically state equation, right? So like very simple only. So what we see, we see that this is the diagonal canonical form. Canonical means minimized, right? Minimum number of state variables. Here, so like yeah, that is this. So what we could have done is here, like instead of like finding the transfer function, then drawing the state diagram and then from the state diagram writing the state equations, if we would have been given the like state equation from starting itself and no transfer function, so what we could have done is basically do similarity transformation, apply similarity transformation to the A matrix, and from there we can find our new equations, right? So what similarity matrix will I multiply? So what transformation will I do? So basically this we have to get to this one, right? The system matrix should be this one. So from that normal system matrix to this one, what I have to do? I have to diagonalize. I have to diagonalize the matrix. Okay. Now if I diagonalize the matrix, then my other things changes. So if I diagonalize the matrix, then what will be my P matrix that I need to multiply, right? So my like D will be equals to P inverse AP, right? So my diagonalized matrix will be that. So what will be this P? If you could remember that P was the individual like columns of eigenvectors, right? Eigenvector columns. Now if that's what I was telling at the start of the lecture, if they are independent, then that's not an issue. So P we can use, right? Now if they are not independent, the eigenvectors in the column format, then we won't be able to diagonalize the this matrix, right? A matrix. Then we have to do other things. Okay, so yeah, that is the main thing. So if we have done the diagonalization, then my new B bar will be simply P inverse B and C bar will be CB, right? CP. So that these things we have already learned, okay, in the previous chapters. From there we understand, yeah, the concept of diagonalization. Okay, so yeah, this was like the brief overview and basic explanation of what we will do. So in gate, right, you will solve like this only. So yeah, that's how you diagonalize. You convert the block into, decompose it into like different transfer functions, okay, individual blocks, and they are contained parallel, okay. That's how you integrate them. Now, right, we have to solve for another question, okay, another question. So here, right, what I will do, like this is again equation of parallel decomposition, but a twist is there. We have to apply parallel decomposition to the following transfer function of a system, okay. Transfer function is given. Draw the state diagram of the system. We have to draw the state diagram, and we have to write the stable state equation of the system, right? Sorry, not stable, we have to write the state equation of the system. So basically all things we have to do. Firstly, we have to apply parallel decomposition to transfer function. So how to apply parallel decomposition? Use partial fractions, right? Use partial fractions. So what is my transfer function? Is this one, right? So how to apply like one thing to notice here is, first thing to notice here is this s plus 2 whole square. So here, right, what are the poles? What are the poles of the denominator, right? Sorry, like it's night and I'm feeling too much sleepy, sorry. So what are the I'm sorry, what are the poles of the transfer function? So poles are -2 and s equals to -3, okay. So these are the poles, right? So one thing I notice is poles means eigenvalues, right? Eigenvalues. So what does this mean? This means these two are repeated, right? Eigenvalues are repeated, then eigenvector may or may not be independent, right? So eigenvalues repeated, so eigenvector may or may not be independent, okay. So this is about the eigenvectors, right? So like now what we'll do, we'll assume that they are not independent and solve accordingly. And if they are independent, then that won't be an issue, okay. Because finding eigenvectors, right, will be a hectic task. Just hold on a second, someone is at the door. Sorry for the interruption. Now let me convert this into our that decomposition, right, partial fraction. So what I will do is this transfer function, right, this transfer function, which is equals to 1 over s plus 2 whole square into s plus 3 will be equals to a over s plus 2 whole square plus b over s plus 2 plus c over s plus 3, right? So these will be my a, b and c, right? Now like I hope you know how to do partial fraction. I will do the shortcut here, and then next step I will tell you the formal manner, how to do it in longer method, right, conventional manner. So shortcut, if you don't understand, that's fine. So what I will do, I will just cross multiply this s plus 2 into s plus 3 on both ends. So what I will get here, this is 1, so this is a into s plus 3 plus b into s plus 3 into s plus 2 plus c into s plus 2 whole square, right? So like now what will be my ABC? If you know, then try to find it and verify, cross verify, right? So what will be my ABC? So right, what I can do is first put s equals to -3 then this one will go to 0 and this one will also go to 0, and this will only remain. So this will be c times minus 3 plus 2 whole square equals to 1. Okay, so c will be equals to 1. Okay, c will be equals to 1. Now what you will do, put s equals to minus 2. Okay, if I put s equals to minus 2, this will be remain light because this is not going to 0. This will be going to 0 and this will be also going to 0. So we'll have a into 1 equals to 1. So this is a equals to 1. So a equals to 1 and c is also equals to 1, right? Now how to find b? So b, right, what you can do is equate the coefficients and then find b. So I will tell you the method of, like, this method you can find all the three variables a, b and c, but as I don't have b, I have to use this equating the coefficient of method just for finding b also. Else what you can do is, like, there is another other method, that is the differentiation. Okay, that also you can do, but I will use this method. So what I will do here is equating the coefficients. Okay, so I will equate the coefficients, right? So now what I will do is, basically this was my equation, right? So I'll copy this and expand this, right? Copy this and expand this. So what is, like, this is left hand side is 1, right? So what is the coefficient of s square? What is the coefficient of s square in the left hand side? Like, if I have some s square term in the left hand side, what will be the coefficient? It will be 0, right? Because I don't have any s square term on the left hand side. So the coefficient of s square will be 0 times s square. And what will be my coefficient of s? It will be again 0 times s. 0 times s, and we have 1, right? So this is 0, this is 0. Okay, and we have 1. Okay, so yeah, this is basically my left hand side. Now I will expand this right hand side in terms of the coefficients of s, right? So first I will expand this one. Okay, this will become, let me bring this down actually, this will become s plus 3 times a plus, this is like, I will expand this directly, ps square plus 5b s plus c plus, this is basically cs square plus 4cs plus 4c. Okay, so this is that. Okay, so now, right, now what else do we have to do? So now I will clump the s square terms, s terms, and the like the constant terms, right? This is a constant term. So if I clamp those two, so here, right, the s square terms are s square b plus c plus, I will now clump the s terms. This is a plus 5b. Okay, another s term I have plus 4c, and again the constant terms, right? Constant terms are 3a plus, this is, okay, this is also 6b. I missed there, this one, right? This one is 6b actually. So let me put this a bit side actually. 3a plus 6b plus 4c. Okay, so yeah, this is basically my equation, right? Now what I will do, I will equate the left hand side, the coefficient, right? Coefficient of s square is b plus c, but in the left hand side, what is the coefficient of s square? It is 0. So from this equation, b plus c will be equals to 0. Okay, so b equals to minus c. So like c was 1 only, so my b will be minus 1. Obviously I'm explaining it to you, that's why it is taking so long, but if you do it by yourself, then this won't take that much long. Okay, but also if you do it only with this method, right, so all three coefficients you will get, okay, just in one go. So now like let's cross verify. Let's put the value of a and c and check if this is coming 0, because here on the left hand side the coefficient of s is 0. So what is a is 1, b is -1, so this is -5, 1 plus 4, so yeah, this is getting 0. So it is correct. Again, let's put the value of abc here. So a is 183, okay, b is -1 and c is 1. So this is 4 plus 3, 7, 7 minus 6, which is 1. Again, our like the left hand side is same. Okay, so left hand side is same. So yeah, this is basically one method you can do. So let me write the transfer function. Okay, transfer function is broken into three parts, right? First part is this a by s plus 2 whole square. So this is s plus 1 by s plus 2 whole square minus 1 by s plus 2 and plus c by s plus 3, and c is 1 only. This is s plus 3, okay, c by s plus 3. So yeah, this is basically my transfer function. Okay, this is basically my transfer function. Now, right, what I'll do, I will draw the state diagram of individual ones, right? So the first question is done. Okay, I have parallelly decomposed them. Now I will draw the state diagram of the system, okay, individually. So this is the 37 now. So my this is my, let's name this as, okay, let's name this as t1, because first I will solve the like non-square term. So t1 of s, and this is the t2 of s, and this is the t3 of s, right? So what we will do, so my t1 of s, right, what is my t1 of s? T1 of s is 1 by s plus 3. Okay, so again solve using the CCF formula, basically controllable canonical form. So like you should be able to do this rightly, but still we'll solve this slowly. X naught of s, okay, divided by 1 plus 3 s inverse x naught of s. Okay, so how will this look like? So we have one state variable basically, okay, one integrator, which is 1 over s here, and this is let's say r, or was this the input r or what? Forgot. Okay, input they haven't told us, so I will take u. Okay, you should be comfortable with both u and r. They are just names and variables. Don't get confused with r and u. Okay, so this time, right, I will take u. Okay, so that you don't get confused like why you are writing unit step. It is not unit step, this is unit, this is input. Okay, so this is y of s. Okay, this is 1 by s, and we have a feedback of -3, right, as this 3 will go in the right hand side. So yeah, let me write here in terms of ratios. So this will be my y1 of s upon u of s, right? Okay, y1 is the first output, so yeah, this will be my -3. Okay, and this is s inverse, and u is coming here with 1 gain, and output what I have with 1 gain. Output also is 1 gain. Okay, as this is the 1 times 1 multiplied by this, so y1. So this is y1 basically. Okay, this is y1. Now let's solve it for the second transformation. So what is the second transformation? t2 of s is basically minus 1 by s plus 2 this time. So if it is minus 1 by s plus 2, so what does this become? So this becomes s inverse x naught of s divided by 1 plus 2 s inverse x naught of s. Okay, and this is equals to y2 of s upon u of s only, right? So this one, and again we have one state variable again, right? How is it incoming? It is incoming like this one. Okay, this is the bracket, this is not the bracket actually, sorry. So this is -2 again, and this is 1 over s again. Okay, this is u of s again, and this is y2 of s. Okay, and now, right, now the gain here is 1 only, because this is 1 only. Okay, and here, right, here the gain is -1. Okay, gain is -1. So these things I will not explain further. Okay, I have already told you all this in the previous lectures. Okay, so now the interesting part. Now the interesting part is I have to find for the third transfer function. Okay, and what is the third transfer function? It is basically 1 by s plus 2 whole square. Is there something in similar to this? So if I break this down, right, this is s to the power minus 2 x of s, okay, x1 of s, and this is basically 1 plus 2 s inverse whole square x of s, right? This is equals to my y3 of s over u of s. So one thing I notice, what do I notice is I've already this term, right? I've already this one with respect to u of s. What I need is just to multiply another 1 plus 2s, like 1 plus 2s s inverse with this one. So I will get my the bottom transformation, right? The bottom transformation I will get. Okay, if I just again multiply this block, right, this block, if I again like multiply, okay, I will get my bottom transformation with respect to u also, right? And the top one, right, top one is s inverse like s minus 2 whole square. So what I have to do is simply, right, I have to add another integrated block. Okay, add another integrated block. So let me draw the block diagram. From there I will explain it to you how I am solving this, right, how I am drawing the block diagram. So first, right, what I will do, I will copy this one, take this one, okay, this will go away. So this one, right, this one will be like this one, okay, and again I will have another choose the size. Actually, this one will come over here, okay, bit down, and this y, right, y will come like this, y will join here, okay. Now, right, what I will do, I have over here x of minus if this is like this is, if this is x of s and this is x of s inverse, right? So what I will do, I will take this one, okay, I have to draw this in different, like, smaller pen. I take this one, right, with gain 1. Now again I multiply the same block, okay, same block I multiply, okay, I use this pen. This is 1 over this, and this is minus 2, okay. And what do you get here? Like, what we'll do is directly connect the output of this one, right, with the, well, like, not with y2 is this one, connect the output of this one with, and what is the gains of this one? So what was the gain of this one? This one was 1 only, and this one also was 1, like at the output, right? Here what is the gain? Gain is 1 only, right? 1 only, right? That's why here the gain was minus 1 and here the gain was 1 only, right? 1. So now we will take the output. Here we will take the output. This is my y of s, okay, and like what you are saying is this is x of s, right? This is x of s inverse, and what will this become? This will become x of s inverse whole square. So here I am getting that x of s inverse whole square, this term, right? Okay, now my output is connected, that is not an issue. Now what about the input? Right, input is here only, okay, input is here only. This is also 1, okay, this is also 1, and this one, right, is getting multiplied by two times, right? This is one block, okay. Let me assume like these are in cascade, right? This is one block, okay, and what is the transformation? It is basically this one, right? This one. Now again I'm multiplying with this block. Okay, again I'm multiplying with this block. That is the same transformation only, like this one. Okay, that's why I don't need to connect this again. Okay, because I'm using the same block, so I will use again here. I will not connect with this one, right? So I'm multiplying with this transformation, then again the same transformation I'm multiplying, so that I'm getting a square term, 1 plus 2 s inverse. This was only 1 plus 2 s inverse without any square, this with square, right? That's why I have to multiply with this again, and then I'm connecting with the output due to this equation. Okay, now what is the homework for you? The homework for you is solve this state diagram. Okay, I'll write this here. Solve state diagram. I will solve the state diagram. I mean solve the S of G basically using Mason's gain formula. I will provide you the notes, okay, and there I will write the solution. So just check if the transformation we were getting is coming same or not. So from there you will understand, yes, this method is correct. Okay, so Mason's gain formula. Okay, from there you will understand this method is correct. So like so whenever, right, repeated like denominator comes, this one, okay, repeated eigenvalues come, you do it like this. You start from top, which are unique eigenvalues, then you go to the bottom. Okay, you go to the bottom, then you write this the first one, which is like the first basically s plus 2 term, this one, right, power 1 term, then you go to this one slowly, right, slowly go to this one. So like this is the s plus 2 whole square term. Okay, this will be in the bottommost area. Okay, so yeah, that is basically how you draw the state diagram for the system. Okay, this is the state diagram of the system. Okay, so yeah, this was the basic procedure. Now what we will do is like this is the homework, solve it, or you can pause it now and cross verify right now itself. Okay, so yeah, just see the state diagram and solve it for yourself. Okay, so now what I will do is basically solve the state equation. Okay, state equation. What will be my state equation? So my state equation, right, again, right, the same procedure we follow, right? What procedure do we follow? Remember what procedure do we follow? So let me like delete this x of s here. Okay, it's very more cleaner actually. Procedure that we follow is name the state variables, remove the initial conditions. So there aren't any initial conditions, so I will just name the state variables. How I will name it? I will name it according to particular convention to get my Jordan matrix format, right? Jordan format. So Jordan canonical format form basically. So what I will do is I will start from the bottom, right? I will start from the bottom and name that as first state variable. So this is just a convention. If you follow, that's well and good. If you don't, that's doesn't matter. But you will not get the Jordan format. The rows and columns will be just like transpose, interchange. So you have to take the transpose to get Jordan canonical form, right? So that is just a difference, nothing else, nothing else. So this will be x1, this will be my x1 dot, this will be x2, this will be my x2 dot, this will be my x3, and this will be my x3 dot, right? So what I will do is subtract this 1 by s terms. Okay, subtract the 1 by s term. Okay, sorry, not subtract, remove the 1 by s terms, because I've already taken the effect in time domain. So this will be changed with u of t and y of s. So u of t, don't get confused again with step, right? This is y of t. So now let us write the state equation matrix directly. Okay, directly. So this so you should be accustomed with this now. So let me write the matrix. This is x1 dot, x2 dot, x3 dot. So let me like what will be this? So this, right, this is basically so what is x1 dot equals to? X1 dot equals to 2 times minus 2 times x1. So this is one value, and x2 times 1. Okay, x2 times 1. So it is also related with x2, but is it related with x3? No, x3 doesn't have any path to come to x1 dot, and u also doesn't have any path to come to x1 dot. So this will be 1 here. Okay, that is the difference. If it would have been able to diagonalize this, then this would have came 0, right? Only the diagonal elements are non-zero and other elements are 0. So this is 1 0. Okay, and what is x2 dot? X2 dot equals to this minus 2 times x2, and is there anything? There is u also, but that I will write later. Do I have x3? No, x3 isn't will not able to connect, and x1 also will not able to come, right? Because the flow is opposite here. So we'll get 0, and this is again minus 2 and 0. Okay, now what is x3 again, right? X3 u is connected, and x3 minus 3 into x3 is connected, but other variables, right, we can't come back to that. So this will be 0 0 minus 3. This will be x1 x2 and x3. Okay, plus simply now u, right? U is connected with x3 dot and x2 dot, and x1 dot is not connected. So this will be 0 1 1, and this is u of t. Okay, and now, right, what is my y of t? Y of t, right? Y of t is simply like this one. Y of t is connected with x3 times 1, x2 times minus 1, and x1 times 1. So it will be 1 minus 1 1, and the state vector matrix basically. Okay, x1 x2 x3. So yeah, this is basically my matrix. Okay, so this is how you solve this. So what do you notice? This one, right? So in Jordan canonical form, what happens is above the repeated eigenvalue, right, we get a 1. Okay, we get a 1. Okay, that is what basically the Jordan canonical form tells us, right? So yeah, this is what my Jordan canonical form is. Now let's go for the cascade decomposition, right? Sorry, not cascade, sorry, cascade decomposition. How do we do cascade decomposition? So in cascade decomposition, we'll do this with a question. Basically, what is the question asking us? Draw the state diagram and the state equation of the following block diagram using cascade decomposition. So the block diagram is already shown in terms of a cascade, right? Because these two blocks are connected in cascade. What do you mean by cascade? The output of one block is connected to the input of another block. Okay. In state diagram also that will do. When we convert this into state diagram, right, the output of the one of the state, right, will go to the other state. Basically, we'll convert these blocks into SFG, right, signal flow graphs. Okay, so yeah, we have been given the transfer function, and we have to draw the state diagram and state equation of the following block. So this is very easy. So like I know I have already derived, but still I will derive it again. So if two blocks are connected in cascade, what will be my overall transfer function? Tell me, what will be my overall transfer function? My overall transfer function, right? My overall transfer function will be simply this. This will come out to be r times h1, and now this will come out to r times h1 h2. So my c, right, what will my c equals to? C will be r times h1 h2. Okay, so c of s over r of s equals to h1 of s into h2 of s. Okay, h1 of s into h2 of s. Okay, so this is my c by r. So in cascade, what happens? The transfer function gets multiplied. So what is my h1 of s and h2 of s? So h1 of s is 1 by s plus 2, and h2 of s is 1 by s plus 3. So what we have to do? Simply we have two blocks in cascade, right? We have to simply convert them each in CCF format. Solve them individually in CCF format. So yeah, that is basically that. Now, right, what more else is we have to do? We have to convert the, like, basically as I told, right, cascade, right? So output of the previous SFG to the input of the next SFG. That is the main thing. So what will my state diagram? So let me do the state diagram basically. I will first solve for one transfer function, then I will go to the another transfer function. So first I will solve from the input side. Okay, let's say that we can interchange this, but let's say the input is connected with this one. So input is connected with this one, how will my SFG look like? So this is bread and butter for you. So basically, right, let's say, okay, what did I choose input? Here I choose input as R. So this is R of S, this will be 1, right? This will be 1 by S, and this will be minus 2. This is minus 2. So, and this is now this will be my output basically. Okay, output is 1 only. Okay, because the numerator is 1 only, and this is going to the other state, right? This is, I hope you understand. I did this very quickly. This is 1 by S plus 2. Okay, you should do this, right? Now I will not write this or something. I will step jump, right? Because previously I've explained it in very brief manner. Okay, so, or detailed manner, as you say. So this is again now we're coming to the next state block. Okay, next SFG. So this is 1 by S plus 3. So this is the input for me this time. So input is connected with 1 only. Okay, it will be 1 multiplied, and then like S has coefficient of 1. Now we have one integrator, 1 by S. Again this is coming back. Okay, loop minus 3, and again this is the output, right? 1, because the numerator is 1 only, right? So that's why I solve it very fast. So this is Y of S only. Okay, so this is my Cascade decomposition state diagram will look like. Okay, now let's do the state equation. Okay, state equation. If I do the state equation, right, so the state equation basically again the same thing, right? I have to assume state variables. So what I will assume, like this one, I will assume that this is my x1, this is my x1 dot, this is my x2, this is my x2 dot. So I hope you remember, right? Just before and after the integrator we write our state variables, right? So yeah, so again I will remove the integrators. Okay, I will remove the integrators basically. And this will be in time domain. So this is basically R of t. Okay, and this is Y of t. Okay, so yeah, this is basically my x1 x2. So now, right, let me write directly the state matrix. Okay, x1 dot and x2 dot, what is it equals to? So x1 dot and x2 dot, right? So x1 dot is minus 3 times x1, so this is minus 3. And is it relative to x2? Yes, x2 is going here, right? x2 is coming over here, so it will be equals to 1. Okay, this is 1 because x2 is coming over here. Now what about x2 dot? So x2 dot, right, minus 2 into x2. Okay, so this will become here, and x1 dot, no, it is not related with x1 dot, so this will be 0. Okay, this will be 0. Okay, now this is x1 and x2 only. Okay, as there are no further forward paths, right? That's why I can write this directly here. If there were multiple forward paths, okay, from the same state variable, then we have to think about that. Okay, that's why. So like this, all this we have done in previous lectures. So now u, right, u, x2 dot is related, not u, r, x2 dot is related, but is x1 dot related? No, u, r can't come here, right? R can't come here. Okay, that's why this will be 0 and this will be 1. Okay, and this will be my R of t. What about y? R can't come. Okay, x2 also can't come, only x1 can reach y. So my y will be equals to y of t. One comma 0. Okay, and this will be my x1 and x2, x1 x2. So this will be my x1 x2. Okay, so my like r so x1 will come over here, and this is not related with input, so D matrix will also be 0, right? So this is to keep note. My like A matrix, right, it will not be in some standard form, it will be weird. Okay, A matrix will not be in standard form. Okay, so yeah, just checking, this is like x1 is coming from here. Okay, yeah, and x2. Okay, yeah, that is fine. And also x2 is also coming to here, and x1 Yeah, that is fine. Two variables. Okay. So yeah, this was it for this question. Now let's solve another question. So this is another question. Now you might ask that here my numbers were simple, right? I could have easily broken it down into factorize it, right? What if I am not able to factorize it? Then how to convert it, right? Now again the same question. We have two blocks which are in cascade, but what if I'm not able to factorize it? This is factorizing, this will be hard, something imaginary will come. Okay, then how to solve this? No worries. Okay, what we'll do is solve this using CCF and solve this using CCF. So for this individual block, the CCF will have two indicators, and for this block the CCF will have one indicator, right? Now pause this video and solve this. Okay, then connect them with input and output, then find the state equation. Okay, so yeah, that so I hope you have paused the video and solved it. So now I will solve. So basically, right, my transformation, right, this is 2s plus 3 times s plus 2, right? So what I will assume, this one as 1 and this one as 1. Okay, solve this using CCF and solve this using CCF. Okay, both of them individually I will solve. So how to solve this using CCF? So let me write this here, state diagram basically. So what will be my state diagram? So my state diagram, right, is, let's say y1 upon r. Okay, this is t1 of s. Let me write the s functions also. R. So this will write, what I will do is simply take common the highest power and multiply by dummy state variable. So this will become 1 plus so this is what my y1 upon r of s into x of s is basically, right? So this is what it is. Now how to draw the state diagram? So this one I may do it a bit slow. So my r of s equals to this, right, xo of s plus xo of s. Okay, I will not write the s again, so this will be a bit confusing. Okay, you understand that x is there, right? Like, sorry, s is there. It is a function of frequency, that you understand, right? Else things will become very messy. So this is 2s inverse. I'm just expanding the denominator, right? 3s to the power minus 2. Now what is my xo? X equals to xo minus 2s minus 1 plus 3 s minus 2 plus r. Okay, plus r. So now right, I hope you understand, right? So this xo has two components. Okay, so we need to have two integrators, right? Two integrators. So we have one input and two indicators and then output, right? So this is, let's say this is one bias and this is one bias. So as we are converting CCF, so this will be directly connected, right? Directly connected. Okay, so or you can put a gain of 1 over here, then you can connect, that's not an issue. Okay, you can put a gain of 1 then connect, it will not make much of a difference. This will become my output then. So if I assume this to be my xo of s, this will be my xo of s inverse, and this will be my s to the power minus 2 x of s, right? So let me put all this in top. Okay, so right now what will happen? Now basically, right, what we will do is we have to multiply minus 2 with s inverse x of s to get xo. So this will be minus 2 only. Okay, now what else we have to do? We have to multiply minus, this is minus 3 into s inverse x of s. So we have to do, again I take a different color. minus 3 into s inverse x of s to the power minus 2 x of s. Okay, so this is my basically state diagram. So this is my r of s basically, and this is my y1 of s, right? And this, what is this gain? This gain is simply 1, right? And this is s raised to power minus 2 into x of s. Exactly, that is what I have here. So this will be gain 1. This will be gain 1. Okay, this will be my gain 1. Okay, so this is how my state diagram for this one will look like. Now the other state diagram is easy only, right? The other state diagram, what is the other state diagram? This is 1 by s plus 2. That is easy only. Okay, so what I'll do, I'll copy this one and connect the output of this one to the next state diagram. Okay, so this was needed for explanation, so that's why you don't need to do imaginary terms, just solve it like this one, right? So now, right, what I will do, I will delete this. Okay, delete this, delete this, delete this also. I will connect the output of this one to the next state diagram. So I will draw it directly here. You understand how do I do it, right? So this one was 1 only. Okay, let me reduce the thickness of my pen. So this one will be, again, this is the input, right? 1 only. Then I have one integrator 1 over s, and what else do you have? This is again my output, right? This is 1 only. Okay, so yeah, what is this gain? This is, it was 1 by s plus 2. So what will be this? This will be minus 2. So let me divide this, right? Let me write it like this so that you will understand this, right? This is one of the transfer functions and this is the other transfer function, right? Okay, so this is my r of s and this is my y of s. Okay, so this is my state diagram basically. Okay, this is my state diagram. Okay, so now, right, now let's solve for the state equation. So I hope you understand how I wrote the state diagram. This one is straightforward, right? Just convert the 1 by s plus 2 into this form, and this one was a bit difficult, that's why I solved that. Okay, you take that, now you expand this, then you solve this, right? So yeah, so now, right, I will solve for the state equation. State equation. Okay, so again the same procedure, right? What I have to do, I have to remove initial conditions. Initial conditions isn't there, so I have to write the state variables, then remove the 1 by s terms. So I will write the state variables basically. Let me choose a color. What color should I choose? Green. Yeah, so this one I will choose as, again, x1. This one will be x1 dot, this one will be x2, this one will be x2 dot, this one will be x3, this one will be x3 dot. So whenever there are two back-to-back integrators, what you can do is simply like connect them with gain on 1. Okay, so if you get confused, so you can do that, right? This is x3 dot, okay, and this is 1 again, so this was 1 only. Okay, I didn't write 1 here, so this is 1 only, right? So this becomes like r of t and this becomes y of t. So this is r of t, this is y of t, and we have to remove 1 by s, right? We have to remove 1 by s. Okay, okay, now just let us do it directly now. Okay, so can I do it directly? Let's see if I can do it directly. So this, right, I will write this here only. Okay, let me do solve it slowly. Okay, so this x1 dot, what are the equations? This x1 dot, right, x1 is coming, okay, and this x2 is coming, right? X2 is also coming. Anything else is coming? No, x3 isn't coming. So x1 dot equals to minus 2 x1 plus x2. Okay, that is what my x1 dot is. Now what is my x2 dot is equals to? my x2 dot, right? X2 dot is this one. Now x2 is not coming. Okay, x2 is not coming because this doesn't have a forward path. rt is not also not coming. x3 is coming, right? x3 is coming, only x3 is coming. Okay, so only my x3 will come. Now my x3 dot, right? x3 dot is equals to what it is, rt is coming, and my x2 is also coming, and my x3 is also coming, right? So x1 is not coming, right? x1 is not coming because it is against the flow. So this will be minus 3x2 minus 2x3. Okay, and plus r of t, right? So minus 3x2 minus 2x3, and we have r also. So now now what is y of t? Y of t, simply only x1 has the path, right? As this is opposite, none of them can come here, right? This is opposite, right? Opposing the flow. So y of t equals to x1, right? So now let us write the state matrix format. Okay, this is x1, this is x2, this is x3. Okay, and this is what let me first put on the broader all those things, then I will write the values. This is x2, this is x3. Okay, this one was dot, sorry, dot plus this is the B matrix, and I have R of t, and here I have y of t. Okay, C matrix, okay, and D is 0 because like output is not connected to the input. Okay, so like what will be my E matrix? So it will be from here, you write it minus 2 1 0. Okay, and this is x dot is like only 0 0 1 0 0 1, and this x dot is minus 0 minus 3 minus 2 0 minus 3 minus 2. Okay, and what is my R of t? R of t is what is this R of t? R of t is like related with only the x3 dot, so it will be 0 0 1. Okay, and what is my y of t? Y of t is only 1 0 0, only related with the x1 of t. So as you can see, right, like these are fine, but A, right, A is not in standard format. A is not in standard, not in any standard format. So A not standard form. Okay, so yeah, basically that is the like end of this lecture. Okay, and that is the end of like decomposition, all those things. And in next chapters what we'll study is basically what do we say, controllability and observability, right? So I will revise all the things in the next lecture, like revise a bit of what happened in the previous this lecture, right? I will revise it because this lecture has already gone long. Okay, so yeah, thank you for watching.